So this section is about hyperbolic functions. So back when we talked about trig, the basic trig functions are actually what we call circular functions. And I'm not going to go into a lot of detail on it, but if you remember the unit circle, on the unit circle, what does the x-coordinate represent? Cosine, and the y-coordinate sine. And any angle that we pick theta to be a specific angle, for example, 30 degrees, the x-coordinate is cosine theta, the y-coordinate is sine theta. And we never did write it quite like that, and I'm not going to go into a lot of detail, but these two equations that I wrote at the end, those are what are called parametric equations. There's like a third parameter that if you give me that parameter, I can plug into those equations and I can tell you the x and y coordinate that correspond to that parameter. And we're going to do some of that in Cal 2 when we get a little bit further. One thing that we'll do as an application of that is sometimes we describe particle motion in terms of time. If you tell me how long something has been moving, I can tell you its x position with some function, and then its y position with another function. Those are called parametric equations. Well, since these parametric equations here form a circle, those are called circular functions. The functions we're going to look at today are called hyperbolic functions. And they're basically parametric functions that give us a hyperbola. So the first of these functions is what's called, the way we name this, hyperbolic sine. And it looks just like sine except we put an h in there. Sometimes instead of using the full name hyperbolic sine, we'll pronounce it cinch. Like hefty cinch sack. Y'all old enough to remember that commercial? Okay, I forgot how young y'all are. Okay, cinch. And it's defined by e to the x minus e to the negative x over 2. Hyperbolic cosine is e to the x plus e to the negative x over 2. And the other 4 hyperbolic functions are just related to those. Hyperbolic tangent is just sinh divided by cos, or hyperbolic cosine. Hyperbolic cosecant is still the reciprocal hyperbolic sine. Hyperbolic secant is still the reciprocal of hyperbolic cosecant, and hyperbolic cotangent is the reciprocal of hyperbolic tangent. So if you can remember, okay, hyperbolic sine is e to the x minus e to the negative x over 2, and hyperbolic cosine is e to the x plus e to the negative x over 2. If you remember how the regular trig functions work, then the other ones, the hyperbolics, work the same. The same reciprocal relationships exist, the same sine over cosine for tangent relationship. Oh, yeah. Thank you. Secant's 1 over cosine. Cosecant's 1 over sine. Cotangent's 1 over 2. And if you were to, and I'm not going to do this, but if we were to write a parametric equation where our x coordinate is hyperbolic cosine of an angle, and our y coordinate is hyperbolic sine of an angle. When you were to plot that, you would get hyperbola. If you were to let theta be from 0 to 2 pi, that's what you would get. That's why they're called hyperbolics. Now, what you need to know is basically this. Now, they give some graphs of hyperbolic sine, hyperbolic cosine, so forth on page 384. Some of the identities are the same, but they're not all the same. Where in regular trig, sine squared plus cosine squared is 1. In hyperbolics, hyperbolic cosine squared minus hyperbolic sine squared is 1. And I'm not going to have you learn all of these identities. They're on 384. If you wanted to take a look at those. But you still have your sum and difference identities, your Pythagorean identities, which are Pythagorean identities, that's just one of them. We still have the other two. They're a little bit different. Tangent, hyperbolic tangent squared plus hyperbolic secant squared is 1 instead of having a minus in there. But I guess what we really want to know is the derivatives. The derivative of hyperbolic sine is hyperbolic cosine times u prime, which is just like the regular trig function. The derivative of sine is cosine. Well, the derivative of hyperbolic sine is hyperbolic cosine. The derivative of hyperbolic cosine is almost the same, except we're missing a minus. Remember, the derivative of cosine is what? Negative sine. Well, for the hyperbolics, you don't have that negative. The derivative of tangent is still hyperbolic secant squared. The derivative of cotangent is still negative cosecant squared, except they're hyperbolics. Another one that the sign is different is for secant. The derivative of secant, remember, is secant tangent. Well, for the hyperbolics, it's negative hyperbolic secant, hyperbolic tangent. Of course, if it's more than just x, you have to use a chain rule, so you prime on the end. Cosecant's the same. The derivative of cosecant is negative cosecant times cotangent. Same thing for hyperbolic. The derivative of hyperbolic cosecant is negative hyperbolic cosecant times hyperbolic cotangent, which makes our integrals, our antiderivatives, are just the opposite of these. So the antiderivative of hyperbolic cosine is hyperbolic sine. The integral of hyperbolic sine is hyperbolic cosine. The integral of hyperbolic secant squared is hyperbolic tangent. And then we just have to remember if any of those are definite integrals and we need to evaluate them, just remember what hyperbolic sine means. E to the x minus e to the negative x over 2. Hyperbolic cosine, e to the x plus e to the minus x over 2. If you have a cotangent, then it'll be e to the x plus e to the negative x over e to the x minus e to the negative x, because it's cosine over sine. So let's work in an example or two. Let's say we have the function hyperbolic cosine 8x plus 1. And we want to take that derivative. Then the derivative of that, basically it's a chain rule. We have an outside and an inside function, so the derivative of hyperbolic cosine is hyperbolic sine times the derivative of what's inside. And what's the derivative of the inside? 8. Let's do that one. What's one rule we're going to have to use there? How do we take the derivative of natural log? U prime over u. So the derivative of natural log, this goes on bottom. The derivative of that goes on top. What's the derivative of hyperbolic sine? Hyperbolic cosine. Cosine over sine, cotangent. Let's do what's the rule we're going to have to use to do that derivative? Product, we have a variable times another function. Use our product rule. If we call that u and v, it's u prime times v plus u times v prime. What's the derivative of hyperbolic cosine? Hyperbolic sine. So that's u prime v plus uv prime, then minus this derivative. The derivative of hyperbolic sine, hyperbolic cosine. Notice what happens with the first and the last terms. Yeah. Cosh minus cosh cancels. So we end up with x times hyperbolic sine. So let's just do this. If we want to find the slope at x equals 2, we substitute 2 into our first derivative. 2 times hyperbolic sine of 2, which, remember, hyperbolic sine, that's e to the x minus e to the negative x over 2. And what are we plugging in for x? 2. So that's e squared minus e to the negative 2 over 2. So our 2's would cancel. So we got e squared minus e to the negative 2. Which is fine like that. If you were bored, you could say, well, that's 1 over e squared. So if we get a common denominator, if I put an e squared here, I'll need an e squared there. So we'd have e to the 4th minus 1 over e squared. Which you could just take and put in a calculator and get as a decimal if you wanted. Which you could have done that here. All right, let's do an integral. Let's integrate hyperbolic secant squared 3x dx. So fortunately, I'm going to give you all these integrals. So the integral of hyperbolic secant squared well, that's weird. That one's not on that front tear out. It is. I was just making sure the sign is correct. I was going to look to see if they're all on the front, but it is tangent. Sometimes I have to flip back just to make sure about the signs, because the signs aren't always the same between the regular trig and the hyperbolics. But yeah, the integral of hyperbolic secant squared is tangent, hyperbolic tangent. So what is our u? Our u is 3x, so what is du? 3 dx. We have our dx, but what are we missing? We're missing a 3, so I need 3 1/3. So basically what we have is hyperbolic secant squared u, that's du, into hyperbolic tangent u, where our u is 3x. It's an indefinite integral, so plus c. Real fast. Okay. So that's our regular hyperbolics. Just like regular trig has inverses, so do the hyperbolics. Now, hyperbolic sine is e to the x minus e to the minus x over 2. The inverse of hyperbolic sine is natural log x plus the square root of x squared plus 1. Now, I'm not going to make you learn what all of these inverse hyperbolics are equivalent to. The inverse hyperbolic cosine it's very similar, except x squared minus 1. So I'm more interested, I do want you to know what hyperbolic sine and what hyperbolic cosine are. I'm not as worried about, do you know what the inverse hyperbolic sine is equal to, what the inverse hyperbolic cosine are equal to. What I want you to do, though, is know how to take the derivatives. How do we take the derivative of inverse hyperbolic sine u? It's u prime over the square root of u squared plus 1. Of inverse hyperbolic cosine is u prime over the square root of u squared minus 1. And let me just pull up the ebook and show the rest of these. These are on 389. So this is the last set of derivatives and integrals for this chapter. Now the derivatives is not a big deal. If you run across inverse, hyperbolic, cotangent, it's hard enough just to say. Inverse, hyperbolic, cotangent, you just take the derivative of your u over 1 minus that squared. If it's inverse, hyperbolic, secant, it's minus the derivative of your u over your u times the square root of 1 minus u squared. Those are pretty much straightforward. If we want to take one of those derivatives, we just find our u and substitute our u and our u prime in. But what's a little bit more or less straightforward are the integrals. Remember, we had integrals before that involved u squareds and a squareds. We had, back in the last section, we had an a squared plus a u squared on bottom. Here we have an a squared minus a u squared. So basically a constant minus a function. That's something squared. We had a du over q times the square root of, what is it, u squared minus a squared. Here we have an a squared minus u squared, or it could be a squared plus u squared. We had a du over the square root of a squared minus u squared. Here we have an a squared, or u squared, minus a squared. So they're flip-flop. So in evaluating, okay, what formula am I going to use? Am I going to use one of these? Or am I going to use, let me go back. Or am I going to use one of these? we're going to have to evaluate, okay, what's u squared, what's a squared, and which one comes first. If my u squared, if I have a u squared minus a squared, I have to look, okay, is it going to be this one, or is it going to be the one that we looked at previously? And what's going to make the difference is whether we have a u out front or not. On our inverse hyperbolics, notice for our u squared minus a squared here, our u is out front, but on 389, let's just do this. When we have u squared minus a squared, there's not a u out front. Here we have an a squared minus u squared. We have a u out front. On the previous ones, when we had an a squared minus u squared, there was not a u out front. So it's going to be a matter of picking, okay, what's a squared, what's u squared? Okay, once I find out what u squared is, what does that make u? What does that make du? Do I have a u out front, do I not? So it's going to, there are quite a few formulas in here that look very similar. So the trick is going to be keeping all of these straight. So let's do an example. Let's look at this one. So under the square root, if it's one of these a squared, u squared business deals, then a squared is always going to be the constant part, u squared is going to be the variable part. So what is our a? A is 1. What would u be? Right. If u squared is this, that would make u 2x, which would make du what? 2dx. So notice if we do that, if u is 2x, notice we have a u there. So on bottom we have a u, the square root of an a squared minus a u squared. And we almost have du. What are we missing to get du? 2. So if we had a 2 here and a 1/2 out front, then that would be 2 dx, which is du. If we compare our formulas on 389 and 378, the one that has du over u square roots of a squared minus u squared, that's the one that's on 389. Du over u square roots of a squared minus u squared. Here. So notice that's what we've got. Where we're using the, ours is minus, so we're going to use the minus. So when we have a plus and a minus over here, we're using the minus. So that gives us, we already have our 1/2 out front. From here, then this integrates into that, which is minus 1 over a. And what was our a? 1. Natural log of a plus the square root of a squared, 1, minus u squared 4x squared all over the absolute value of u, so the absolute value of 2x. And then all of that gets plus c. So basically, positive times negative, we have negative 1/2 natural log of 1 plus the square root of 1 minus 4x squared over the absolute value of 2x plus c. So it's just a matter of substituting into our formula once we figured out what our formula was. Ours was du over u square roots of a squared minus u squared. Okay, we found that formula, so this is what that integrates into. So I just have to substitute in my a squared, u squared, and u. Let's do another one of those. Let's do this one. Now we have one that has an a squared minus u squared. We have one. In the last section, we had an a squared plus u squared on bottom. This section, we have an a squared minus u squared on bottom. So if we're going to use this one, what would our a squared be? Yeah, our a squared would be 9, so a would be 3. Our u squared would be x to the 4th, so what would u be? X squared. So what would that make du? 2x dx. So we have an a squared, we have a minus, we have a u squared, and what are we missing to get du? We're just missing a 2. So we can put it multiply by 2, divide by 2. So we have 1/2 the integral of du over a squared minus u squared, which if we compare that to our formula on 389, that integrates into 1 over 2 times a times natural log of the absolute value of a plus u over a minus u plus c. Aren't you glad you don't have to memorize all of these? I should have waited to the end of class before I told you I was going to give you all a formula sheet. It'll make y'all sweat a little bit more. But this is why I'm going to give you a formula sheet. I don't have all these memorized. I don't care to have all these memorized. There's no point in having all these memorized, because if you happen to have a book, let me see if I can find where they start. Starting on page A3, there is a table that goes through A6 that has 99 different integration formulas in it. And none, well, I say none, most of those 99 are ones that we haven't ever even looked at. Now, some of those are repeats of things that we've done, but a lot of them aren't. So, in short, there are a lot more integration formulas than there are derivative formulas. So, when it comes to integration, if it's beyond one of our basic ones where it's a natural log or an e to a power or a u to a power or one of our trig ones, then you're basically going to either look at a table or look at a formula sheet and try to figure out, okay, what can I pick for u to make it fit one of these formulas? For this test, we're not going to have that table in the back of the book. We're just going to have all of the integration and derivative formulas that we've used so far. So let's do another one, I reckon. Let's look at that. Now, one clue that you might have to complete the square on some of these is if we've got more than just a constant and a variable squared. If we've got a variable squared and a variable, then we need to make that part into u squared. So we need to complete the square on that part so that it's x plus something squared. Because right now, that not only does that not factor, but it definitely doesn't factor as a perfect square in its current form. So I'm going to take this plus 8 and move it over. So what would I need to add to this to make it a perfect square? 4. Half of that, half of 4, and then squared. So 2 squared is 4. Of course, if we add 4, we also need to subtract 4. So how does that part factor? X plus 2 squared. X plus 2 times x plus 2. Then the part that's outside of the parentheses, but still under the radical, that's plus 4. So we have u squared and a squared. And remind me, how do I know that this is the u squared and not the a squared? Because that has the variable. So what would that make u? That's what's being squared, x plus 2, so that's u. What would that make a? And what would du be? Dx. So we have du. That's u square roots of u squared plus a squared. Du over u square roots of u squared plus a squared. As long as they're both positive, it doesn't matter which one we write first. We could write the a squared first. We could call that 4 plus that. But do y'all agree, though, that that's that with a plus? And in fact, on this one, we don't even have to multiply by anything to make our du. So that integrates into minus 1 over a, natural log a plus square roots of a squared plus u squared over absolute value of u plus c, where our a is 2. So the natural log of 2 plus square roots of a squared is 4. U squared is x plus 2 squared. U x plus 2 plus c. Fortunately, on the problems in 5.8, there are not very many different things to pick for you. it's pretty much, okay, I've got a u squared and an a squared, so this has got to be u. Well, just what I have left, give me my du. Then I'll look and see, well, which formula is that? So I've given you a list of those to do for homework. I've also given you a review from this chapter to do for homework. In lab, you want to finish up your project, and then let's work on WebAssign to try to get some practice with those while I'm still around. So if you want me to help you with some of those, I can. Now, I know on Monday, y'all three are going to be, are all three of y'all going? Yeah. Oh, you're going on vacation, but y'all two are going. And then y'all three are going. So basically, y'all two and Evan will be here. We're probably going to go ahead, I've told them already, we're probably going to go ahead and do one section on Monday. And I'll do a video lecture of that and post that on Blackboard. And Caleb's going to take his test tomorrow, or do you want to take it when you get back? Okay, Caleb's going to take his test, and then we'll schedule to do the rest of y'all's when y'all get back.